Let's start with this quick reminder. We have three vectors, you see them here, green, red, and blue. Let's look at the green. The green is given this expression. It's A sine theta. So if we are going to draw it in an xy axis, measuring the angle theta counterclockwise relative to the x, and since my amplitude is A, I draw an arrow with a length A, making an angle of theta with the x-axis. Now, a vector that's going to be ahead by pi over 2, we just add 90 degrees to the green one. So we have 90 degrees here, so this full angle is theta plus 90 degrees. If it is behind by pi over 2, we just do the opposite. So we are going to have 90 degrees here. So we have the blue angle is actually theta minus pi over 2 or theta minus 90 degrees. Remember a couple of other things as well. Whenever I have a vector like this, I can figure out the x-coordinate and the y-coordinate of the vector. For example, for the red one, the x-coordinate is going to be this. This is my a sub x. And the y-coordinate is going to be this, a sub y. Now, the y-coordinate is actually, it's a sine theta, it's a sine of this angle, whatever that angle is. In this case, is theta plus pi over 2. The x component is going to be a cosine of that angle. So for this one, for example, it's going to be a times sine of that angle for the y component, and a cosine of that angle for the x component. Now, why did we have this review? That's because of the quantities that we use for RLC circuits. Consider these three voltages. The voltage across the resistance, which is in phase with the current, is given by VR max, which is R times I max, sine of 2 pi ft. Now 2 pi ft is my theta in this case. VL is I max XL. It is 90 degrees ahead of VR. So this is theta plus pi over 2. VC is VC max, which is I max XC, times sine of 2 pi ft, my theta, minus pi over 2, since it lags by pi over 2. Graphically, if this is my VR, this would be my VC, which is 90 degrees behind, so it's going to be here. And this is going to be my VL, which is 90 degrees ahead. Okay. Now, the difference between this graph and this graph is the fact that our theta is going to depend on time. So, for example, pull in the simulation. In this case, the colors are slightly different. So, where we have green for VC, blue for VL, and red for VR. And let's reset it. So, VR is making an angle theta. VC is 90 degrees behind VR, and VL is 90 degrees ahead. And as time progresses, you are going to see this is progressing. See it, it is rotating. Note the following. As I play it, the vectors are going to rotate as time increases, and they're going to rotate in the counterclockwise direction. Remember, the red is VR, green is VC, it's lagging behind, and leading up front is VL. Notice the values here, XC, XL, and R. They are given. They depend, of course, on the frequency that's in the bottom here if we scroll down, and they depend on the capacitance, inductance, and resistance values. Now, look at the maximum voltages. VC max, it's XC times I max. VL max is going to be XL times I max, etc. The RMS values, the same as the max values over square root of 2. Notice the overall maximum voltage across the generator. Notice it's not the sum of these three. What we talked about before. Imax is 1.118, so all of these are VC max is going to be XC times Imax. VR max is 50 times Imax. That's the way we get this value here. Now, the impedance, square root of R squared plus parenthesis XL minus XC squared, that's here. That's the reactance of all of them together, or what we call the impedance. In this case, it's 107 ohms. This delta here is the angle that the generator voltage or the overall voltage is going to make with the current. In this case, it's a negative number in radians, indicating that it is lagging behind. And it is lagging behind because the capacitor voltage is bigger than the inductor voltage. We have more lagging voltages than leading voltages. As we run it, I'm going to run it in slow motion now. Now notice for every instant, the values of the voltages are going to add up. This is the graphic like what we saw earlier. This is rotating as we expect. This is VR at this particular instant for 0.00035 seconds. This is VL. This is VC. This is the sum of all of them, the black one. Okay, the way you get it is going to be, and we'll talk about that later, it's going to be this minus this, and then this at this angle, you are going to have the parallelogram there. But you notice in here, the values are shown here. Overall voltage is 116 volts, which is VR, which is about 38 volts, and then VC, which is at this time a positive voltage of about 110 volts, and VL, which is in this case about minus 31 volts. So when you add these three up, VR, VC, and VL, you should be able to get the 116. That's the voltage across the capacitor, across the generator, the overall voltage. Now, as I increase the time, you notice all of these, they maintain the same length since they are the same Vmax values. That's what we are showing here. But their amplitude, what we are reading in here, is what's changing. The voltage, the instantaneous values are changing. And the overall sum, since the instantaneous values are changing, the overall sum is going to be changing. So that black arrow is changing.